Now when we have understood how the heat engine and the Carnot cycle works, now we will be using the concept of Carnot cycle to come up to the idea of entropy. Okay. So, it always mesmerizes me how people came up with the idea of entropy. So, in order to understand how they actually came up with this idea of entropy, we have to again go back to the efficiency of the Carnot cycle. So, this is why like the Carnot cycle is so important, because it gave the answers to the heat engine, the efficiency. It set the maximum limit to the theoretical maximum limit to the efficiency of the heat engine, and then now with the use of this, now we know that we are going to come up with the idea of entropy. Okay. So, to define entropy, let's start with this concept of the efficiency of the Carnot cycle. So, we knew that the efficiency of a Carnot cycle is given by Th minus Tc by Th. We derived this in a previous video. Okay. Now, we also know that the efficiency of a system is the efficiency of the Carnot cycle was given basically by the amount of heat that you gave to the system in the denominator, and in the numerator you have to find out the amount of net work that the system produced. Okay. So, this is how this is how you calculate the efficiency of any steam engine. Okay. Any heat engine, if you want to calculate the efficiency, you calculate the amount of heat given, and you take it in the denominator and you calculate the net amount of work that was done. Okay. Now, everything that is below in here that I have already written has been like derived in an earlier video. So, that is why I took the liberty to write all those equations. Okay. So, we've calculated that the W net in that Carnot cycle came out to be the function like this. So, R ln Vb by Va, V's are the volumes, and Th and Tc's are the temperatures of the hot and the cold system, and this was equated to be equal to Qh minus Qc. This came out to be true. Okay. So, this whole value was this. Okay. Now, how did we get that? So, let's go back to how we just try to recall how we calculated the value of Qh. Okay. So, Qh was basically Q1, which was the first step of the Carnot cycle. Or how was the Carnot cycle? So, I'll just draw it once more. So, you have V on this side, you have P on this side. Okay. So, the Carnot cycle was something like this. So, it's something like this. Okay. Now, you started from A and you move like this. The volume here was Va and the temperature here was Th. The volume here was Vb and the temperature here was Th again, because the process 1, the step 1 that we had here was an isothermal expansion. So, in isothermal process do not change the heat, do not change the temperature. So, you have the same temperature in here. Process 2, the step 2 was an adiabatic expansion. In this case, you have an adiabatic expansion, the heat amount of heat remained the same, but the temperature dropped to a value of Tc and you have Vc. The step 3 was again an isothermal process, but in this case this was an isothermal compression. Okay. Step 3 was an isothermal compression. In this isothermal compression, the temperature again remained constant and it remained Tc and the volume was Vd. Okay. So, this was the general this is the general Carnot cycle, and this we have discussed the different individual steps in the Carnot cycle in a previous video. So, okay, now in here we want to calculate what was Qh or Q1. So, this was the first step in which you gave an amount of heat which was equal to Qh, and we wanted to find out what that Qh was. We came up with this idea that Qh became equal to W1. Why was this case? So, if you remember, in the first law of thermodynamics tells this, right? The first step in here was an isothermal expansion. Is an isothermal process that the temperature does not change, and therefore the internal energy do not change. Okay, so internal energy in step 1 became 0, and therefore Q became equal to W, and therefore we have it Q1 is equal to W1, and this Q1 was basically equal to the amount of heat that was given. So we found out the amount of work done, W1, which is equal to Q1, was equal to RTHLN VB by VA. We have calculated this before, and we have numbered this equation as equation number 37. Similarly, for step 3 now, what we did, we tried to calculate the amount of work that was done. Okay, so the amount of work that was done in here was equal to the Q3 with the same logic again going, because step 3 is also an isothermal process. So Q will become equal to W. So again Q is equal to W in here, and this was QC because it was an exothermic, because heat was released in this. Okay, so that's the negative sign. So this became equal to RTC ln VD by VC. VD and VC. So these were the volumes. Now we also calculated that there was a relationship between these 4 volumes, VD, VC, VA, VB. Now we calculated these in terms of 2 adiabatic equations, because we knew that there is a relationship between the volumes, and that was given by T2 by T1. If you have any adiabatic equation, then you have this thing valid. Now we use this formula to for both step 4 and step 2, and we calculated that VD over VC is actually equal to VA over VB. Therefore, if you have a VD over VC here, we can just substitute that as VA over VB. Also, if we just want to interchange the numerator and the denominator inside this natural log, then you will have a minus sign coming up in here. So basically minus of QC is minus RTC ln VB by VA. So when you actually see this W net, so this thing comes out to be QH minus QC. How? Because you see QH is basically R ln VB by VA into TC. You can see here QH is exactly this equation, R ln VB over VA times TH. Okay, R ln VB over VA times TH. Now minus of QC came out to be minus of RTC ln VB by VA minus of RTC ln VB by VA. So basically the W net came out to be equal to QH minus QC, and we will be using this in here. Okay, so this came out to be QH minus QC over QH. Okay, now if you simplify this, it comes out to be 1 minus QC over QH. If you do a similar thing in here, this comes out to be 1 minus TC over TH. Okay, now if you have these true both equal to eta, that means that this function is equal to this function, like 1 minus TC over TH is actually equal to 1 minus QC over QH. Now if we have this, if you take these two, then you will have TC over TH is equal to QC over QH. Now if you interchange this, if you want to take this and come to the, if you want to take TC and bring it to this side, and you want to take QH and bring it here, so you get a QH over TH, this is a subscript, becomes equal to QC over TC. Now this is a very interesting result. This says, and we'll name this, we'll number this as 49. What this means is, although in a cyclic process, this was a cycle, like it was a Carnot cycle, although in a complete cycle the amount of Q was not a state function, right, because the amount of Q was changing as you moved across the cycle. But interestingly, when you have Q over T, that quantity is kind of behaving like a state function. Like see, like this quantity is getting preserved. QH by TH is equal to QC by TC. That means the quantity Q over T is behaving like a state function now. Okay. Now this is extremely important. Like what was the state function? This which the quantities that do not depend upon the state. Like if you come, the quantities that only depend upon the initial and final state and do not depend on the path taken. So although q was a path function, q over t becomes a state function now. It starts to behave like E or like enthalpy or internal energy. Now this is extremely important. Now this is from where we get the idea that the q by t becomes a state function, and therefore for any cyclic process, for any reversible cyclic process, like this was a reversible cyclic process, the quantity q by h now becomes a state function. Now we will now see that this quantity is conserved for any kind of reversible cycle. Now since this quantity is conserved in this particular reversible cyclic process, we will now see that actually Clausius, he came up with this idea that not only that this q by t quantity is preserved in the Carnot cycle, now he said that q by t is conserved in any type of reversible cycle. So our next stop will be to find out how q by t is conserved in any kind of a reversible cycle.